Chi-square 2, goodness of fit. All right, chi-square, goodness of fit test. Again, that's for testing whether scores break into certain categories in the way we hypothesized. We're going to ask a question here. Does birth month affect success? This is something I read about in one of Malcolm Gladwell's books. I kind of followed up on this and did my own analysis as well. There were some studies that examined birth months broken into three, and I break them into 3-month period here for elite athletes. This was first with national youth soccer players in Europe. Starting at a relatively young age, people begin to train with the national teams in many European countries for soccer. They found that overwhelmingly these players tended to be born January through March. Well, why might this be? Well, when you start, recruiting people to soccer to national soccer teams around 12 or 13 years old, the kids that are born in January might have a significant advantage over those who were born in December of the same year. The way that the league years work, it's simply what year you were born in. So the kids who were born in December are going to be can be almost a full year younger than the kids who were born in January. That might not make a difference when you're in people are in their 20s, but it can make a huge difference at 12 or 13 or 14. Really, a lot of change can happen over that time. What these authors noted is that those early advantages, they don't get made up for, because the kids who are chosen for the early national teams are the ones who get the training, and that all feeds into them being successful down the line. And we've already talked about this piece, how you've got some players that are older than others. I tested the same prediction on the U.S. national under 15 team, and you can check this out yourself. This I did a couple of years ago, but it's held every time I've looked at it. So there were 32 players on the team. 16 of them were born January through March, so already we're seeing half. 8 were born April through June, 4 July through September, and 4 October through December. The question we want to ask is that surprising given our null hypothesis? Get our null hypothesis, nothing's going on, which would mean that we should have an even distribution of players across these different periods. So the null hypothesis is that birth month makes no difference. If that null hypothesis is true, we would expect an equal number of players born in each 3-month period. So we'd expect 8 players to be born in each period. That's going to end up being our expected frequency. The observed frequencies are what the data actually show. The expected ones here are what we would expect if the null were true. So here's the observed frequencies listed next to the expected frequencies. We just plug these 4 values in into our chi-square formula. You can see we've got 16 minus 8 squared over the expected frequency of 8, 8 minus 8 squared over 8, 4 minus 8 squared over 8, another 4 minus 8 squared over 8. We simply add this up and it gives us a chi-square value of 12. Well, what do we do with that chi-square value? We have degrees of freedom of 3, and I'll show you where these values come from in a second. Degrees of freedom of 3, if we wanted to do the old school approach, we could go to a chi-square table. This one, what we'd want to line up here is 0.05 and degrees of freedom of 3. That gives us a value of 7.82. And you can see our value of 12 is much larger. Okay. So our value of 12 is much greater than 7.82. So that tells us we can reject our null hypothesis. Of course, we would normally be doing this in R. Since 12 is greater than 7.82, we reject the null hypothesis. A good plain English explanation, players are not equally distributed across birth month. There are more players that are born earlier in the year. Again, remember, one of the big pieces in this class is to always use plain English explanations rather than just saying reject or fail to reject the null hypothesis. All right, doing this in R, you can see the value here. We'll look at some code in the tutorial and in a little bit. You can see if we do this in R, we get the exact same values. We get a probability 0.008 here, or 0.007, I should say. And the correct way to write this up in APA style, chi-square, that chi-square value is not in it's not in italics. We don't italicize Greek symbols. Degrees of freedom, and then the probability. This is an example from the literature. This is an example from a study that I conducted a while back. Down at the bottom 3 rows, we have a chi-square test comparing 6 different groups: white men and women, African American men and women, and Asian American men and women. Again, there were other people in this data set. We just didn't have a large enough sample to really do anything with them. The first question there: personal experience with discrimination. I'm comparing the frequencies in each of these categories, expecting there to be equal numbers of people who had an experience with discrimination. Not surprisingly, African American men and African American women reported more often having experiences with discrimination. Surprising to no one. You can see the chi-square value is 33 there. There's a value called V next to it, which we'll talk about in a little bit. And I guess we're going to talk about it now. The value V is the effect size, Kramer's V. Sometimes this will be listed as phi, the Greek symbol phi. It's interpreted much like a correlation. It's basically on that same scale there.